Welcome to the Explainer. Today, we're basically going to build a superpower, the ability to predict the future. Well, okay, maybe not the whole future, but the future of anything that moves in a straight line, all by using the fundamental language of physics.
And I mean everything, from galaxies swirling out in the cosmos to the blood pumping through your veins right this second. Even when you're totally still, the universe is in a constant state of change, of movement.
So, how do we get a handle on all this? That's the core question of kinematics. It's the language physicists came up with to describe movement, even before we start asking why things move. So let's get started and learn the vocabulary of this pretty powerful language. To really get this predictive power, we have to start with the words, the basic vocabulary. We're going to kick things off with two concepts that sound simple, but in physics, the difference between them is absolutely crucial.
We use speed and velocity pretty much interchangeably all the time, right? But for a physicist, that little extra piece of information, the direction, well, that's everything. It's the difference between your GPS saying you're 5 miles away and you're 5 miles in the wrong direction. Velocity has both a speed and a direction, which makes it what we call a vector.
Think about it. Your car's average velocity for a whole trip might be 50 miles per hour. But what that needle on your dashboard is pointing to right now, that's your instantaneous velocity. The real question is, how in the world do physicists measure something at a single, tiny, fleeting instant?
Well, this slide shows a really clever trick they use. If you look at this table, as the time window we're looking at gets smaller and smaller, from 2 seconds down to 1, down to 1/100th of a second, the average velocity stops jumping around so much. It starts to zero in on a single precise number, 3.84 meters per second. It's like we're using a mathematical zoom lens to find the true velocity at that one specific moment.
Okay, so we can nail down an object's velocity at any given moment. But let's be real, motion is rarely that simple. Things are always speeding up, slowing down, changing direction. And the word for that change? That's our next key concept.
And that word is acceleration. The best way to think of it is as the change agent for motion. Anytime you hit the gas, slam on the brakes, or even just turn the steering wheel, you are accelerating.
So this is the really big takeaway here. Acceleration isn't just about speeding up. Because velocity includes direction, any change in your speed or your direction counts as acceleration. So get this, a car driving in a perfect circle at a totally steady 30 miles per hour is constantly accelerating. Kind of weird, right?
All right, we've got velocity, we've got acceleration, we have our tools. Now we get to assemble the ultimate cheat sheet. These are the kinematic equations. 3 simple-looking formulas that let us predict the future for any object as long as its acceleration stays constant.
Let's start with a basic question. Say we know an object's starting speed and direction. We know how it's accelerating, and we know for how long. Can we figure out its final velocity?
You bet we can. And this first equation is basically just common sense written down as math. It just says your final velocity is whatever you started with, plus all the extra velocity you picked up from accelerating over time. Simple, but incredibly powerful.
Okay, what about distance? It's great to know how fast something is going, but can we predict where it's actually going to end up? What's its final position or displacement?
Yep, our second equation nails this one down. And it's cool how it works. It basically has 2 parts. The first part figures out where the object would have ended up if it just cruised at its starting speed. And then the second part adds on all the extra distance it covered because it was speeding up the whole time.
Now, this is all great if you've got a stopwatch, but in the real world, you don't always know exactly how long something's been moving, right? Is there a way to connect velocity and distance without needing to know the time? And you know what? There totally is. This third equation is kind of the magic one. It cleverly combines the first two to get rid of time completely. This lets us link an object's final velocity directly to how far it's gone, which is super useful out in the real world. Now, I know these can look like just a bunch of letters and numbers on a screen, but they're not abstract. These equations are secretly running the world all around us. So let's look at how they pop up in everything from discoveries made centuries ago to the traffic laws you see every day. Way before we had all these neat equations, Galileo was studying things in free fall. He didn't have a slow-motion camera, but he had ramps and bells and an absolutely brilliant mind. And he noticed this beautiful, elegant pattern in the way things fall. And this is what he found. It's so cool. In each equal chunk of time that goes by, the distance the falling object travels during that chunk
follows the simple pattern of odd numbers: 1, then 3, then 5, then 7. It's just a beautiful pattern that falls right out of the kinematic equations we just looked at. Okay, let's jump back to today for something that could literally save a life. We all know you have to slow down in the school zone, but the physics behind why the speed limit is so much lower is actually pretty startling. Let's use our equations and see for ourselves.
The key is a concept called stopping distance. And when we use our kinematic equations to create a formula for it, you got to pay very close attention to that initial velocity term. It reveals something incredibly important. Did you see it? The initial velocity is squared. That little 2 changes everything. It means if you double your speed, say from 20 to 40 miles per hour, your stopping distance doesn't just double, oh no, it quadruples. That is a massive difference.
And here's the really scary part. That quadrupled stopping distance, that's just for after your foot is already on the brake. It doesn't even account for human reaction time, that critical fraction of a second it takes your brain to see a hazard and tell your foot what to do. This isn't just a physics problem, it's the science that saves lives.
So look at what we've just done. We've put together this basic toolkit for predicting motion. And suddenly, it's like we have a new lens to see the world, revealing this hidden order in everything from a raindrop to a planet. We've shown you the language. Now, what are you going to see with it?